Thank you for the introduction. I'm the second one from UC Davis for this session. And it happens, and the previous speaker, not just from the same department, we're also from the same family. So, and she talked about how we deal with the leftovers. So I will talk about how we can process better food with less natural resources. At the same time, I also work with the USDA, the Western Regional Research Center, that's also in California. So this is the talk is a kind of a review about some of the work we have done recently. So I may not have a lot of the detailed data to show you, but I'll give you some results. The reason we wanted to research about the infrared heating for food processing, because we have the demand, we have the need. One is to produce the high quality and the new products. At the same time, sustainability, it is a very important issue in food processing. We need to save energy, water, and also other natural resources. Some of you may be familiar with the infrared. The infrared wavelength is shorter than microwave and the radio frequency. It also has a less penetration compared to the microwave and the radio frequency. However, the equipment cost is much less than those two different kinds of the technologies. Why is infrared? Infrared offers many advantages compared to some other heating mechanisms. One is because it is a radiant heating, and it doesn't need any mechanism for the heat transfer. Another thing is it can deliver a large amount of heat when we use the processing. At the same time, we can control the amount of heat is delivered. So through the presentation, you will see the technology we developed, it improves the product quality and the safety too. In my lab, over the years, we have developed many different devices related to infrared. And I will show you a few photos in different kind of scales. And I'll get into a little bit more details later on. In terms of the research we conducted, based on the applications, that's including dehydration, blanching, peeling, disinfestation, disinfection, and stabilization. For dehydration, conventional drying or dehydration typically using hot air. It's produce a low product quality, and also drying rate is very, very low. So what we did, we discovered we can use this we call the sequential infrared and freeze drying method to achieve high quality products and also save energy. This is just a regular comparison between the hot air and the infrared drying. What you see, the drying rate, I do not have the laser pointer, so that's okay. You see the line on the bottom, that's the drying rate of the hot air drying. Those lines on top, those are the drying rate of the infrared. You can see the drying rates of the infrared are much higher than the hot air. That's desirable. Also come to the quality, this is the one for the example. You see the infrared dried onions on the left is much wider than the one dried with hot air. It is the better quality from infrared drying. So we have done a lot of the drying study, and including walnuts. What we found, we can use the infrared to do the pre-drying followed by hot air drying. We can save at least 35% of the energy. Right now, we are doing a commercial scale demonstration. And we got a project from California Energy Commission over $1 million. So we are doing the commercial demonstration. Maybe next time, so I'll show you some of the commercial demonstration results. Come back, when we produce crispy snacks, typically use deep fat frying, it's not healthy, or freeze drying. It uses a lot of energy. We developed this as a sequential infrared freeze drying. What we can do, we use infrared to dry the strawberries, for example. We remove 30 to 50% of moisture first, then freeze the product and finish up with freeze drying. We can save more than 30% of energy. Why the product is crispy is good? What you can see the cross-section of the strawberries. The left one is a regular freeze-dried one, and the one in the middle, that's a sequential infrared freeze-dried one. You see a thin layer of the crust on the surface. That's why it produces the product is very crispy. But however, the hot air dried one, all the cells collapsed. It's not crispy. It's not in good quality. Also, infrared can be used for blanching without use of water or steam. Because it's dry blanching, it also can remove water during the blanching process. So that's why we call simultaneous infrared dry blanching and dehydration method. So it's a more energy efficient and also simple process. We combine blanching and dehydration into one single step. And in terms of application, when we buy the juice bars from the store, typically they're made with the juice after remove the fibers. We can use this kind of the method to blanch and also partially dehydrate the fruits, then make a restructured fruit bars. It's much healthier. This is better for the people's health. If we use this infrared blanching and dehydration technology to pre-treat French fries, what we can see, we can get the color very good and also quicker. And what you see, the oil content for the French fries. During the frying, the pink lines, the infrared treated ones, and the blue lines, the regular method people produce the French fry. What that means, at the very beginning, the infrared treated one absorbs the oil faster, then kind of level off. But for the traditional ones, and continue to absorb the water. So we can see we can reduce the oil content in the French fry more than 20%. That is very significant for the industry. Not just say less oil, we also did sensory analysis using different frying time and different temperatures. As a result from the sensory analysis, what we can see, for example, when we use the 174 degrees, more than 50% of people like the French fry produced by the new way compared to the regular French fries. That means from a sensory standpoint, it is also desirable, besides the nutritional benefits. Since we have all these promising results, we built the large-scale demonstration unit used for demonstration of the technology we developed. You see the equipment company for doing some demonstration. We use all the different kind of the fruit and also vegetables to do the blanching and the dehydration test. It worked out very well. What you see here is a slice of the potatoes. As long as we can have right conditions, we can blanch the product with a very high quality. This is the slice the sweet potato, apples, and these after treated, we fried it. Do you see any differences between these two kinds of the chips? And you do. I also too. You see the one on the left, a lot of oil. That's the traditional way, vacuum fried. But the one on the right is the way we did use infrared to blanch and partially dry, then vacuum fry. It is much less oil. We talk about less than 20% less oil. This is more obvious for the sweet potato chips. Not just that, we also dried other fruit and vegetables, especially those the thin slice, try to produce crispy, healthy snacks. We were very successful. The flavor is very good, very crispy. And now we have another commercial demonstration project, over $1 million awarded from California Energy Commission. So now let's switch the topic a little bit for the different application about the almond pasteurization and the roasting. California produces a lot of almonds in the United States, but the concern is about the safety. So there are two different kinds of product. One is after pasteurization, still needed to be raw, taste like a raw almonds. And another type of product is kind of roasted product. What we did for producing the raw almonds, okay, or we call the processed pasteurized raw almonds, we heat the almonds with the infrared real quickly to a little bit above 100 degrees. Then we cool it down and hold it for a little bit. Let's look at the reduction for the salmonella. And if we heat it to 108 degrees, we can reduce the salmonella over 7 logs. Okay, it's a very effective and very successful. Not just the reduction for the salmonella, and also the quality. And we did a quality evaluation, and it just tastes like the raw almonds, no change in terms of the sensory quality. For roasting, right now typically people using the hot air. See, the temperature from 130 to 150 degrees C to roast the almonds takes a long time. It cannot guarantee to achieve 5 log reduction. What we did, we take a similar approach like what I mentioned before for drying, but using high temperature, we call the sequential infrared and hot air roasting. And also we compare with just the infrared roasting and also hot air roasting at the same temperature. This is the roasting time reduction. If we roast the almonds to the kind of what we call the medium quality, okay, and we see significant reduction of the time. And if we use the IR alone, we reduce the time about 70%. That's a lot, right? And if we use sequential infrared hot air, we reduce the time from 38 to 62%. Still, it's a really large percentage. Then the question is, can we get the 5 log reduction? When we look at the reduction of the salmonella, definitely the sequential infrared hot air reduce more than the hot air alone. Hot air is from 3.6 to 5.4, but the sequential one is from 4 to 7 logs. That means it has provide a better way to ensure the safety of the almonds. Now let's talk about the rice. California produces a variety of the agricultural crops. Rice is another thing. Typically, rice is dried with hot air at 43 degrees C. That's the kind of maximum temperature people use in the industry. If the temperature is too high, what happens is the rice can break during the milling process. Problem is it's very, very slow, okay, energy intensive. And what we want to develop a method, say, we can achieve disinfestation, and not stabilize rice during the drying process. Let's see if we can do it. Yeah. This is what we want to achieve, okay? We use the rice with a different moisture, did the drying study. Following the infrared heating, we hold the rice at the drying temperature, whatever the rice temperature, for a certain amount of time. Typically, we found 4 hours holding is good. We call it tempering, okay? That's what we did with the different the drying temperature. Now let me show you some of the results. After the drying, we also did a milling quality study because the quality is very important. It's not just how quickly we can dry the rice. The figure on the left is the rice temperature versus the heating time. We can see the rice temperature increase very quickly. Takes about 60 seconds, 1 minute, to get to 6 degrees C. That's really quick. Look at the moisture removal during the heating process. That's the one on the right versus the rice temperature. Okay? Yeah. What we can see, when the rice temperature at 60 degrees, we removed about 1.7 to 1.8%. Remember, hot air take about 15 to 20 minutes to remove about 2%. This is only 1 minute heating. It is much faster. Come to the quality. This is the head rice yield, the whole kernel rice. What we can see, the blue line, that is the one using infrared heating followed by the tempering and the cooling. Okay, it had a higher head rice yield compared to using the hot air. Okay, that's the ambient air. Ambient air means the better quality of the rice. That's the dashed line. It is better, and also we see the 60 degree is good. Yeah. Besides the building quality and the drying rate, we also did the sensory evaluation of cooked rice. And based on all the results, there's no difference between the new method versus the conventional hot air method. That's good. Yeah. Because I'm an engineer, we do a lot of modeling study and to see what happens during the process. This is the part of the rice kernel. You see the temperature change from the surface to the center. The point P2 and P1, that's the kind of interface between the husk, the rice bran, and also between rice bran and the endosperm. What you see here is the moisture gradient versus the heating time. And the red line is the moisture gradient, and the blue line is the moisture is the head rice yield. So what we see here, when the moisture gradient is too high, then the milling quality starts to drop. Rice will break. So this is good. That's what we want to know. Come to disinfestation. You know, the insects in rice, it is a big issue. And typically there are two types. One is we call the beetles, another called the moth. We use those two kind of insects as indicators to see if during the drying and the tempering process, we can kill all the types of the insects, like egg, larvae to adults. Look at those green rows. So that shows the heating time 60 seconds, get to the temperature about 61 degrees with the tempering, then basically we killed everything. Okay, this is good. And for the beetles, very similar results. And it showed we need tempering and heating. I thought I have 40 minutes. I have 40 minutes based on the schedule. If you look at your booklet. Yeah. That's how I prepared my presentation. Yeah. Yeah, right? Okay. That's all right. So, yeah, but I will not talk 40 minutes. I know it's already late, but I will try to go through my slides quickly, and I know it's late, so, but I just go with the schedule, so try to, yeah.
I'm saying the digital version is 20 minutes, so it's obviously something mixed up there. So we are very tight on time, so if you could do what you can.
Okay.
Appreciate it, I think. Thank you.
Okay, sure. Thank you. Appreciate that. And say about the stabilization. You see, when we start rice, what happens? After a while, the rice will become oxidized, right? That's because the lipase oxidation. So then the theory is, if we can inject the enzyme in the oil, then we can store the rice longer. Then question is, can we use this process to achieve the goal? Look at the free fatty acid in the rice bran, okay, during the storage. What we see, the control sample, that's the dried with the ambient air, increase very quickly. But if the rice is dried with the infrared for 1 pass or 2 pass, that means 2 times. And the increase of free fatty acid is much, much slower. This is a better technology. We have a lot of the new results shows we could store the rice as the brown rice instead of rough rice. Then come to the disinfection. Mycotoxin is the big concern in grain in general. So we choose the aspergillus flavor as the microbe for the test. So my student did all the inoculation and to see the treatment performance. Here we go. What we see the reduction, okay, on the y-axis versus the tempering time. What happens if we tempering the rice for more than 60 minutes? We can get an over 5 log reduction. That means it's good, right? As a result, we did achieve, we can use the infrared plus tempering to improve the drying rate, kill the insects, kill the microbes, and also stabilize rice. I think the technology has a good potential to be used in the industry. Let's switch to another application for the infrared, about peeling. In general, worldwide, people using the light peeling or steam peeling. But the problem is we use water, and light peeling generated the water with high salinity. So ideally, we wanted to have something more sustainable and also only remove the skin of the tomatoes. Okay, that's the desirable way. Now again, can we do it? What you see, we start something relatively simple in the lab. He is my PhD student. Then what you see, the tomato, and this is the 2 infrared emitters. It get heated up, the surface color start to change. Okay. And I'll keep it going, and now let's wait. It doesn't really take long, take about 30 to 40 seconds. Then we'll see the skin cracks. Okay. It's about to crack. Yeah. Anyway, so after the crack, what you can see, the big crack on the surface of the skin, it's very easy to get the skin removed. Very nice, right? The surface is so clean. So that's what you see, the peeled and also unpeeled tomatoes. And also compare the surface of light peeling and infrared peeling. You see very different. The light peeling is on the left with the multiple cracks, but the one on the right is infrared heated tomatoes. So because it's very effective, we started to do more detailed study to evaluate the peeling performance of the technology, such as the peeling ability, peeling loss, the firmness, and the easiness. Yeah. We use all the kind of the instruments to quantify the infrared peeling performance. I want to go through the details, okay, I promise you. So this is the Young's module of the tomato skin, and this is the setup for measure adhesive energy, how much energy we need to remove the skin after heating. And also we use the DMA to analyze the mechanical properties, okay, under dynamic conditions. We call the temperature RAM test and also frequency sweep test. And let's take a look at the dark color dot lines. For the IR peel and the light peel, they are very different. Okay, I want to get into the detail. The same thing for the storage modulus, they are very different, the peeling. That means they are different peeling mechanism as what we have seen. And also look at the microstructure. You see the crack or separation under the skin. Yeah, that's what happened. And also we look at the pericarp tissues and the microscope. And the light peeling, or light heating, and the infrared heating, they are very different. We also measure the rupture strength of the skin. The reason is, as what I have seen, the mechanism is because it's different. It's because the pressure build up under the skin. Once the pressure is higher than the strength of the skin, it will break or will crack. So my student developed the model to predict under certain heating rate how quickly the pressure will goes up, and then we can achieve this crack. And that's not all, because we want to have a uniform heating and also good separation. So my student developed the model of the tomatoes. So we can use the model to predict the heat transfer. And we started from something a little bit complicated by measuring different dimensions. And this is what we have. And we can base on dimension to get this equation. But the equation is really complicated. There are several constants, and they're very difficult to determine. So then what we did, we looked at the coefficients. We found like an A and B affect the shape, the size. And the C1 and the C2 affect the shape of the tomatoes. That's good. That's a good discovery. Then we correlated the dimension to the mass and the height. And it seems like A and B have a good relationship with the mass and the height, but not the C1 and the C2. C1 and C2 more or less is constant for say a specific variety of tomatoes. Now we can simplify the equation and have empirical correlation regression equations to calculate A and B, C1 and C2. Then we can get the something really like the tomato. Okay. Then we did the shape characterization and validate the result. It looks good. So what we predict the mass and versus the measure, and and also surface area too. The model worked really well. Okay, come to the last step for the heat transfer, because we want to have uniform heat transfer. So this is the tomato model and the infrared heating that involves the convection, conduction, and radiation. It's a very, very typical heat transfer problem, but it's very complicated. And this is what happens after 60 seconds of heating. One is the face of the emitter surface, another side is away from emitter surface. So that means they are not uniform. What we need to do, we need to rotate the tomato during the heating process. We validated the model. It worked really well, and you see the predict and the measured temperatures. Okay, we also did the different size and the different conditions. Then we built, this is a large scale unit. We call the pilot scale peeling equipment. Yeah. I do have 1 minute video I want to show you. So this is the unit we built, and also we tested at 2 commercial processing facilities. So what you can see, the tomato are fed to the emitter. So for this unit, we use the electric emitter on top, only one side heating from the top, and it is rolling through to a vacuum chamber. The chamber can help to induce the cracks on the tomato surface. You see they came out from the heating section, get into the vacuum chamber. Yeah. Then you will see the tomato came out from the chamber. You see the skin and the tomato more or less already kind of separate. What we call in the industry called the flax. That's the skin. Then we use what called the pinch roller to grab the skin. Then we can put it off. Then we can get the peeled tomatoes. So now you see fully peeled tomato come out from the equipment. Definitely, we have been working with the industry closely in trying to commercialize the technology. And you see my team at the processing facility. And what you see here, the comparison, infrared peeled tomatoes versus the steam peeled tomatoes. Okay, so you don't need to say anything. It definitely is better quality. And also, the technology can be used for not just the tomatoes and also other fruits too, like the pear. So, as a conclusion, definitely it has many different advantages: improved quality and safety, save energy. So we did add a book a couple years ago. Now it's available. If you are interested in the infrared research, could be a good reference. And some of the results I just mentioned already mentioned in the book. I work with many companies, organizations. I do want to thank them for the support. I used the 29 minutes. Thank you.
Thank you very much. Any question?
Thank you very much for interesting topic. I am interested in using infrared radiation for dehydration. So, in your research, what was the wavelength of infrared radiation you use? Wavelength of infrared you use?
I have to apologize. Can you repeat the question again?
I am interested in using infrared radiation for the dehydration. So,
Use the infrared or heat the resins.
yeah. What? So what was wavelength of radiation? Infrared radiation you in the
You're
study?
talking about the intensity? Are you talking about intensity?
Sorry? Wavelength.
Wavelength.
Yes,
Okay, I got
this is
it.
very important.
Okay, I
Yes.
see. Okay.
And the second question is any chance of bioactive compound when you apply the infrared radiation for treatment? And the third small question is compare between the infrared drying and the combined infrared drying and freeze drying. What is different between the drying efficiency and energy consumption?
Okay.
Thank you.
You're welcome. Definitely, people always ask me what kind of wavelengths of infrared I prefer to use or what I think it should be used. It is a very interesting question. If we look at the water absorption peak, or we look at the absorption peak for the food materials, including proteins, carbohydrate, and definitely there are some of the peaks, and also they are not overlap. But however, if we talk about we are targeting the water, and there is a peak around about 3.2 micrometers. That's what normally feel should be good one to target. That's what we are talking about called the narrow or selective wavelengths, the infrared. In general, for me, what I do think, because energy is very important, and also the equipment cost is very efficient, is important. So I recommend to use the broad wave infrared. So what that means, we can use the infrared with the peak wavelengths targeting the say high peak of the water absorption. That's the first question. The second question is related to chemical compositions. Because the infrared is just more or less like the other thermal processing, okay? And it can cause some chemical degradation for the chemical compounds are sensitive to heat. The third question is regarding the energy saving compare, say, the sequential infrared and freeze drying to the regular freeze drying. We expect, based on all the results, at least 30% of energy saving from the new technology. Did I answer all your questions?
My question is in the dry blanching, which you use for your potato. Do you think the method can work for pulses where maybe you want to extract some soluble anti-nutritional factor? Can the infrared go into the cell membranes of the pulses and be able to extract those anti-nutritional factors, the soluble ones?
So if I understand your question right, you are talking about if we can use the infrared as a system extraction. Is that what you're talking about?
In blanching, there are
Yeah.
two purposes of blanching.
Right.
Either to extend the shelf life or to leach out some unwanted soluble materials or substances in your raw material. I'm asking the infrared technology, do you think it will be able to leach out unwanted, what we call the anti-nutritional substances in pulses, that is legumes? If we apply this technology in blanching legumes, because legumes, we normally use steam blanching to do the blanching. If we use dry infrared blanching, can it perform the same work? That's what I'm asking.
Oh, okay.
Yeah.
As I mentioned, typically in the industry, either people using the water blanching or use steam blanching. When people use the water blanching, and typically water-soluble nutrients can be leached into water, then there is concern about the nutrient loss. Again, so for infrared dry blanching, it is still thermal processing that may cause certain, like I say, vitamin C to degrade. Can we use infrared dry blanching to replace the steam blanching? I think we can, especially for the product after dry blanching can will be further processed. That's my take for your question. Yeah. I'm not sure if I fully answer your question. Yeah.
Does it have the power to leach out?
No, well, when you talk about the leach out, that's what I'm saying. So, if say for the microwave assisted processing, okay, they talk about say help extraction, and in terms of the leaching out, because this is the dry heating, okay, there is no medium around it, okay, except the air. There's nothing leached out. Yeah, yeah.
What she mentioned in the unwanted component in the product, she wanted to leach out removal. It can be removed by the blanching, but it has to be possible to remove this unwanted by using the infrared.
Okay, thank you for the help with the question. No. The reason is, this is surrounded by air, so nothing will leach out. Doesn't matter the good components or the bad ones. No. The answer is no. Sorry. Yeah.
Okay, thank you for your presentation. It is interesting, especially with the peeling method. But my own question is, now that you are using infrared for peeling, and you could see that the skin is intact, that is, the texture is improved, and the color also is improved. Now, did you bother to look at the nutrients? Because at the end of every processing, we want to be able to present a food that is wholesome in quality, in terms of the nutrients being intact to the consumers. So if you just look at the energy savings, what about the nutrients that are in this food? And also you were comparing infrared with conventional drying. Now, we know infrared to be surface heating. Like you rightly said, the penetration is lower than other methods. Now, if you look at that, did you consider the slowest heating point? And if you did, what about case hardening effect? If it will not penetrate so much, why is the surface of the food affected? Would case hardening be a problem?
Good questions and comments. The first thing regarding the nutrient effect. Let's take the peeling as an example. So what we have seen, based on the heat transfer, what we see when we use the infrared, we can heat the surface of the tomatoes, for example, very quickly. But the inside of the tomato still is cool. I'm talking about it's not really heated. As fast as the say steam or light peeling. What that means, the inside part of the tomatoes, and had a lower temperature. That means they should have a better nutrients retained. Okay, so I hope I answered the first question. The second question regarding the heat hardening. That's why, so when we use a sequential infrared and hot air, sequential infrared freeze drying, we produce much crispier products. That's also we are doing the commercial demonstration to produce crispy products. Then the heat hardening, it is an issue, especially when we deal the large dimension products for only drying purpose. That's why when I give you all those examples, you can see they are all the small dimensions. Yeah.
Okay, one last. Yeah. So can we use infrared drying for making raisins?
Very good idea. Actually, I had a postdoc from Turkey a few years ago. We did try to use infrared to do the blanching and also the drying. So what we have seen, it maintained the better quality, better color. So the answer is you can.